Look at myself. I want to see myself. Oh.
Anything else looks great?
No, pero necesito estar madre, no quiero. Make it tiny. So we're like uploading. Oh. Oh, but then if you see this, if you see the screen share, you can't see the whiteboard. Stop share. Okay. I have to pin myself in order to record the meeting. So. ¿Qué onda? ¿Qué hubo? Okay.
No, dale. Ahorita estás pidiendo. Good job, sir.
Nobody else wants to come in? So, good afternoon, class. The first one is an SSB. What does SSB stand for? Single sideband, probably. Modulator operates with a measure signal. MT equals cosine 2 cosine. For I, that's what, 2 hertz. Right? 2 hertz. Yeah. The carrier is given by cosine 25 and sine of 25. This is the message, you know.
Lynette, can you zoom into the board?
I don't know. Oh, that is blurry. Video settings, HD. Oh. What video editor? Good question. Guess I could just write bigger. No creo. De la cámara no. A ver, tal vez con el control, aquí hay control, ¿no? Por ahí. A veces hay control.
Yo he visto que le mueven aquí.
¿Esa madre?
Oye, te digo.
Ay, mi rodilla. No, it's okay. It's only gonna cover like half of it. It's very what are they using? Ahora, ¿dónde le picas?
Soy un mago.
Ya.
¿Qué pasó, güey?
Le pusiste en
Conference.
conference. What is
That worked.
oh shit.
Insulten.
Well, for reference, they try to keep it aligned with the whiteboard.
Tengo un gallo.
Con el projector. Okay. Gracias, Mr. Jesus.
¿Te dejan el cuento?
You get extra credit. Mama, is that you? Okay. So, is it inverted for you, Aaron, or is it right side?
What?
Is it mirrored or is it correct?
I can see it clear. I can see everything clear.
But is it mirrored?
I don't think so. No, no. It's correct. I can see it clear.
Okay. It's for me, it's mirrored, but okay, if you can see it. What is the? Oh, just added error post. Okay, so the message signal is 2 hertz, and the two carriers are cosine of 20 pi t and sine, that's an S. How do I do that? Sine of 20 pi t. That's bothering. The system operation is shown as figure below. So it looks like it's the audio message signal. The Hilbert transformation, you guys remember what a Hilbert transformation is? I talked about it. All it is you add or subtract, I forget, 90 degrees to the current message. So, in essence, let me see what trying to find my notebook. The Hilbert transformation is the only one that doesn't change from frequency to something else. But anyway, let's deal with this problem. I don't know how much important it is to remember what the Hilbert transformation is. Write down somewhere. I don't want to get a wrong information. That's all. Hilbert, aha. So the Hilbert transformation is when you get your regular signal.
Renee, it's out of focus.
Oh, no. What? How did that happen? Did it just randomly happen?
Yeah.
Weird. Yeah, probably. Wait. Okay.
Yeah, that's good.
So the Hilbert transformation is when you get your regular signal, and then all you do to get the Hilbert transform, which is this little half here, is get cosine of same thing, but you take away 90 degrees. That's just a little phase shift. That's all the Hilbert transformation is. Or you can also say cosine of omega minus pi over 2. Okay, so essentially, you're getting the 2 channels there. One of them is doing cosine, the other one's doing sine, but in reality, they're both kind of doing the same thing because they over transform, like changes the phase of it a little bit. But anyway, what's the question? Draw the double-sided amplitude spectrum M, which is gonna be the message signal. Okay. Now it says MT, not MNT, remember? So we look at our thing here. It says double-sided, so it has to be centered at 0. Right? And then we said this was 2 hertz. And there's gonna be one at -2 hertz. This, and the amplitude would be half of that. This is 1. Easy peasy, right? Is that what he said? Okay. Peachy peachy, right? It says MT, that's important, not MNT. Next one, No. Says write the equation in terms of cosine m hat t. So that's this one right here. So we have our mt, now our m hat t is going to be equal to 2 cosine of 4 pi t. Oh, sorry.
Minus.
Yeah. Minus 90 degrees or pi over 2. If you're feeling fancy. That's it. It's also in terms of cosine. Right? Right, okay.
Let's just put this one for that.
This is the Hilbert transform. You can transform. You get your function and then you just shift it by 90 degrees. Pretty cool, right? And then draw the double-sided amplitude and phase spectrum of m hat t. That's this one right here. Green. Okay. Now we get our amplitude diagram, spectrum, whatever you want to call it. Amplitude spectrum. We get our 0 hertz is here. That's 2 hertz. This is negative 2 hertz. Same amplitude for both of them, which is 1. However, the phase this one, oh, we're gonna have to do it in the, we're gonna have to transform it first into the, what's it called? Using the Euler-Stein jig. E to the J, 2 pi. 4 pi. Probably 4 pi. Yes, technically we have an n here. And the n with 2. So we're 1/2 like that. Anyway, let's just leave it like that. Minus 90 degrees plus e to the negative j2 pi t minus 90 degrees. Right. That negative gets distributed here into the both of these. We get plus e to the negative j2 pi t plus 90 degrees. Because the negative distributes. This will stay the same. So we get that for this one, where the frequency is positive, our phase is negative, like so. And where our frequency is negative, our phase is positive. Make sense? Sí, es que si se acuerdan, era cosine, no se ve, ¿verdad? The cosine of MSC is equal to 1/2 of e to the j of x plus e to the negative. Right? That's where we lost the 2 here. From here to here, that's how we lost the 2. Any questions? Nicole, you're being awfully quiet. No, guys, turn your cameras down. Any questions before I delete this? I'm gonna keep this up. So we can refer to it later.
And can you move it to the right just a little bit?
Oh yeah, you can see that?
It's just out of sight.
Make it a little bit smaller. How's that?
I think that's good.
Erase
It
the
says
cosine.
negative J2 pi t.
The omega CT, it's like a basic
Oh.
Euler's identity or Euler's formula. It's something to do with Euler.
Okay.
Well, the double-sided amplitude, okay, we just did that. We did both of them, right? Oh, we didn't do the phase for this one. The phase for this one is pretty much there's 0, there's 2 pi, there's negative 2 pi. Since there's no like phase shift here inside of the cosine, they're both 0. He said, I'm sorry. Okay, so that's that. So double-sided amplitude and phase. Draw the double-sided amplitude and phase of modulator output that. Okay. So what happens when you add the cosine and the sine? I did?
Isn't DMP?
Oh yeah.
It's a single line.
Yeah, I see. So this is from the carrier signal. Okay. Sorry.
You're right.
Sorry. Okay. Can I erase this? Or okay. Well, it's not that it's wrong, it's that the question was read incorrectly. So in a way, the question was wrong. Oh, it's because we did MT, the double-sided spectrum of MT,
Yeah.
message signal. M hat T in terms of cosine, which stayed the same.
Yeah.
We did the amplitude and phase of MT, but then I thought this was the same thing as this, but it's not. It's a little bit higher frequency. So for 1D, for people that can't see me pointing at the television here, 1D. We have draw the double-sided amplitude and phase spectrum of MT times the cosine of 20 pi. They're being multiplied, aren't they? For the problem. So we have our message signal, which is 2 cosine of 4 pi t times the cosine of 20 pi t. And that is difficult, but we can do this together. That's 2 cosine, where's it at? I think it's half. 2 times 1/2 of cosine of gamma plus subtract them cosine of 16 pi t. Is that so?
Yes,
Yes, it's trigonometric identity. When you multiply cosines together, you basically have half of the sum of the cosines plus the difference of the cosines. But this is the hard way. This is the difficult way. This is the way I like to do it, but this is the difficult way. If you remember, a multiplication in the time domain is the same as a convolution in the frequency domain. So all we gotta do is take this bad boy right here, which is 1 and 1, if you recall correctly. Right? We take this back over here, which is same thing, but it's 10 hertz and 10 hertz. And they're both, well, this is actually one, so it's 1/2. Right? And we do the convolution. Easy peasy, right? You could do the trigonometric identity, but don't think, like Dr. Sun says, don't think it's easier to do it this way. So since it's convolution, we're just repeating this signal at both of these frequencies, and it ends up being 10 plus 2 is 12. 10 minus 2 is 8. 1/2 times 1 is 1/2. And 1/2 times 1 is 1/2. And the same thing over here. Negative 10 plus 2 is negative 8. Negative 10 minus 2 is negative 12. 1/2 and 1/2. Right? That's it. But Renee, why is it the same thing? It just is, because if you look here, this becomes 1, right? This becomes, well, hertz. This becomes 8 hertz. There's your 8, there's your 12, and since it's double-sided, you get half of 1 here and half of 1 here. Oh, same thing. What's that?
¿Y el 2 qué le pasó?
La parte de la fórmula. So this 2 here, that canceled out by the cosine multiplication formula, where I believe it's cosine of u times cosine of 3 is equal to 1/2 cosine of u plus 3 plus cosine of u minus 3. See this? So when you multiply 2 cosines, you get half of the amplitude, which is what we got canceled out here. That should have been another color. Man, I'm not used to drawing one.
Pero en este caso, los cosines se deben de tener, ¿no? Then you're like, two cosine and cosine.
That's not mad. I'm not gonna be mad.
Not bad.
I'm not gonna be mad. Where's the question? Okay. So tú, ¿qué pasó?
El 2 ese?
Este 2.
No,
Este 2.
no. Since you're multiplying those two there,
Uh-huh.
yeah, and then you have to take out the 2, but what happened to the other cosine?
Okay, well, this is cosine times cosine. We don't want that. We want one cosine and then sum of another cosine.
Yeah, no, it's entiendo.
Okay.
I know the identity, but that 2, what you did to it, you took it out.
It's right here.
You actually did it. Sí, pero es 2 cosine times cosine, not cosine times cosine.
I know, but it's that property that you can just multiply this first before you multiply this over
Oh,
here.
I see.
So that's the order of multiplication doesn't really matter in the end. I forgot what that's called. I used to know all the identities by heart. Transitive property of multiplication. Yeah. Transient property of multiplication. Allows you to multiply these cosines first and bring the 2 out. That's why you can bring out a constant out of an integral because of the transient properties of integrals. Anyway, any questions? Nicole, Aaron, Carlos?
On the third amplitude spectrum, those 4 numbers are 1/2, right?
Yes.
All 4?
1/2.
Okay, thank you.
Now, the amplitude here is 1. Why are they half? It's because it's double-sided spectrum. If you were to bring them back together, it would be 1.
Okay.
All right. Here's the game. Draw the double-sided amplitude and phase spectrum of m hat t and sine of 20 pi t.
For the face of this, it would just be 0, right?
For what? Oh, for the face of this? The face here, yeah, it'll just be 0. If you were to draw the face spectrum, it would just be 0, 0, 0, because there's nothing here, there's nothing here. Very, yeah. So let's erase this, if I may. The reason I'm using such a small space is so that it can be seen by the camera. Otherwise, I'd be all over the place, like I was in the other engineering building where I was like, all whiteboards. Okay. So the question says m hat t, which we remember, well, let's write it first. M hat t times sine of 20 by t. M hat t is this minus 90 degrees. So that's 2 cosine of 4 pi t minus pi over 2. And this stays as a sine of 20 pi t. Now, we could just plug it out, but I think it's best to like turn this into a cosine first, right?
Yeah.
So, in order to turn a sine to a cosine, I don't remember. I would right. I just don't remember if it was subtract or add 90 degrees.
That's what you wanna move it now.
Yeah. So if you wanted to go from sine to cosine. Right.
This is about that, didn't it?
Yeah, but
Okay.
he's been saying just subtract 90, so just subtract.
Yeah,
So the sine is like this, and the cosine is like this. Right? So you want to move the sine to the left 90 degrees. So wouldn't that be 20 pi? Oh, wait, no, you're going to cosine, so it's be, yeah, it'll be minus 90 degrees. Minus pi over 2. Right? Makes sense. You have a cosine, but you want it to be the same value as this, you move it to the right. Over 2 times, okay. Well, now you multiply them. Same thing happens. We have to do the same formula over here. Then we go 2 times 1/2. Sum of this, which is cosine of 24 I t. Sum of this is pi minus pi, right? And then you add the cosine of the difference, which is 4 minus 20 minus 16. I t difference will be 0. That stays the same. And that's it. Then the question says draw it. So we have our amplitude here. This one's 12 hertz. This one is 8 hertz. So we can go 8, 12, negative 12, negative 8. And their amplitude is all of them going to be 1/2. And that looks identical to the other one before, isn't it? Again, this is the hard way. We could have done it the easy way afterwards, but that way we can visualize what happened to this space here. By doing it like this. And now for the phase diagram, it's asking for the phase diagram. Yes, for the phase spectrum. We have to draw the exact same frequencies. At negative 12, which is here. I like to do it. I like to transform it into an exponential first so that I can see what happens to the phase. This one becomes e to the, let's say, to the 12 I t j minus pi plus negative j I. Negative gets distributed, I forgot the E. Negative gets distributed, so at 12 hertz, at positive 12 hertz, we have a negative I. And at negative 12 hertz, we have a positive I. So remember that the phase diagram should be symmetrical about the origin. So if this is going down, this is gonna go up. And for the 8, this one, it's E to the negative J, oh sorry, positive J. Oops. To the J negative 16 I T plus negative J to the negative 16 I, or that's it. So for positive 16, 8, not 16, 8. Sorry, 8. For negative 8, the base is going to be 0. For positive 8, the base is going to be 0. Because once again, there's nothing here to shift that part of the signal. So this is the phase spectrum, and this is the amplitude spectrum. Also. Now this is maybe negative pi, but in reality, isn't it the same thing? Negative pi is the same thing as pi. Whatever. Sun will kill you if they're not symmetrical about the origin. And these have to be symmetrical about the y-axis, what is it, amplitude axis. Questions? Draw a double-sided amplitude and phase spectrum of modulator output, MT cosine and M hat T sine 20T. So this plus the other one that was before, which is identical, but different phases. How would that look? Huh. Let's find out. What does it kind of see? Okay. If we recall, the previous one looked something like this. It was 2, 1/2 cosine of 24 I T. There was no phase. Plus cosine of negative 16 I T. There was also no phase. It was negative. Was it negative? I think it was negative. Therefore, all we have to do is add this and add this. This is positive. All we have to do is add this and add that, and we're done. Right?
Yeah, it is the negative on the other one too, so it's 4 minus 1.
Right. Maybe I was wrong. Maybe I was wrong there. I think it's negative. Anywho, this is equal to M hat T times cosine, times cosine of 20 I T. And this up here is equal to MT without the hat times the sine. What's backwards? Yeah, what's backwards? This is sine. Sine, and this is MT times the cosine of 20 I T. So all we have to do is add this, add that, and we get, so the amplitude is 1 for all of them. So we get cosine. Cosine of 24 pi t plus cosine of 24 pi t over the phase shift which is minus 5. Plus cosine of negative 16 by t plus cosine of negative 16 by t. Which is just equals to double that. However, it's cancelled out.
Which one?
These two.
They should, because they're like 90 degrees, right?
They are 90 degrees, they're 180 degrees out of phase with each other. So these two go to 0, and all you're left with is this much. It's 2 cosine of blah blah blah. Is that what he put on this when he was working on it?
I had done it, he gave me 100 on it, but he also said in class, just because we got 100 doesn't mean it was right. So I don't know if mine was right, but I think that's what I did.
You made it equal 0?
Yeah, I had that equals 0 and I had 2 cosine. The negative 16.
Yeah.
I lost my paper, so I'm not sure, but
So nobody was here when he was doing this one? Nobody was paying attention during this? Damn. Well, I think this goes to 0.
because we was doing the review, skip this one. So it was.
Súmalo, súmalo.
What?
Súmalo, súmalo.
To get this? Let's prove it. Let's scroll.
Tengo también, there's some like activities that say, the plus or minus.
Yeah, I know that one, but I was trying to figure out how to use it. We have cosine of 24 pi by 8 plus cosine of 24 pi 8 by 8 minus 5 equal to 0. Yeah, 0. So according to symbol lab, this goes to 0. This right here. Because they're the same signal and this second half is out of phase by 180 degrees. They're destructive of each other, so they go to 0. Now you're left with is 2 cosine of negative 16 times bada bing, bada boom. And the question was, I don't even know if I'm answering the question anymore. The question was, draw it. So, this is the only output. So we have our 8 and our 8 hertz. And the amplitude is 1. That's it. That's the answer for 1F. Questions? Yes. In this case, yes, basically 0. Nicole's gone. Or is she trying to get in, but I haven't noticed?
She was driving.
Okay, where does she live? Far or far city far?
No.
City and far. That's okay, we've been recording this, I can put it on YouTube unlisted, and I'll share the link to you guys later. No questions? We can move on.
What are you?
YouTube?
Only for latest market.
Yeah. I could just leave it listed. But then you guys would show up, no, one way you don't show up. It's only me, only your voices show up. So YouTube, if you're watching this, the entire classroom is full. Because I am a very good teacher and everyone loves to listen to me. Don't forget to like, comment, and subscribe, and click the notification icon so you can get videos whenever they come out. Alright, with the song. Okay, an FM modulator, we're starting with question number 2, so we can get rid of this.
Poner la cara de son, así con nada.
We can write down this over here with our formulas. Hilbert transformation is x of t equals cosine of omega t x hat t equals cosine of omega t minus pi over 2 yeah, that's the Hilbert transformation. I'm gonna take this down. I guess I could write down the cosine multiplication again. Cosine of u times b. No. Cosine of u times cosine of b is equal to 1/2 cosine of u plus b plus cosine of b minus b. Okay. An FM modulator operates to the output. It's the output. What are we doing? Perfect. So XCT is equal to XCT is equal to 10 cosine of 200 pi t plus b t. Modulator operates with an FB of 1 hertz per volt. Let's write that down. It's 1 hertz per volt. And the message signal is MT. This looks like just a bunch of formulas we're going to use. 10 cosine of 20 pi. It's just a tone. The modulator is followed by a bandpass with a center frequency of 100 hertz and a bandwidth of 50 hertz. So we'll worry about that later. Thank you already for this question. Yes. No, I got here at C, right at C. So what's the phase deviation? You could look at the PowerPoints. Let me pull up my laptop so it's real. So funny. Guys, no phones in class. If I look like I gained 10 pounds, I did. I ate a Golden Corral. Just Thanksgiving. It's great. But that wasn't a good first.
I just bought like a scale, and then I weighed myself, out to Thanksgiving, bro. I was like, 180, 183, 184. You know, after it was 187. Oh, sweet. I was like, that's fair.
Pero qué delicioso. Esa qué agusticidad. Oh, hey. Okay, so this part will be cut out of the YouTube video. We're putting this on YouTube. You're late, by the way. We're putting the sign in. Okay.
That's why I recommend.
Okay.
That shit works. Yeah.
What works?
I feel like I'm sorry, bro. It's like,
So right now we're taking a break because I'm trying to pull up the PowerPoints. But after that, we'll be back in business. Back in business. I'm doing my best.
No, it's fine, yeah, I appreciate that. But. I couldn't see.
Okay, we're dealing with phase deviation. I think that falls under population analog, maybe? Sideband, single sideband generation, maybe? Deviation. Where is it? Okay. Phase deviation is phi t. Okay. FD is, what's FD? What the heck is FD?
I think it's that one.
FD, you're looking at? Oh, you can see,
That
okay.
equation.
So frequency deviation constant in hertz per unit of message. Okay. So if it's asking us for the phase deviation, we were given the frequency deviation, but not the phase deviation. Okay. Does that everybody understand that point? They gave us this, which is the frequency deviation. Now we want our phase deviation, which is in terms of AF. And I believe I remember him saying that it doesn't matter if it's in radians or degrees. But in this case, we'll use degrees. Okay. So it doesn't matter as long as it's consistent. So we know that KF is equal to, according to the power point, KF is equal to 2IF. LRFD, which is 1 hertz per E, which is volts, I'm guessing, and 2 pi. So our KF is equal to 2 pi hertz per volt. However, when you multiply by 2 pi, you might get radians per second, blah blah blah. But this is it. Pretty sure. So let's just yeah. No, it's actually. Hold on. We just got our KF. Sorry, KF. Now, in order to get phi t,
Roll 10 cosine 20 pi t.
oh, slow down. We have our this. I don't know what this is.
Sure, that's something.
But this is whatever. Equals KF
Okay.
integral t. Maybe I'm not greedy. That's are they both alpha? Yes. Okay.
And then, we did 2 pi.
We know what KF is. KF is 2 pi, right? This is from the beginning to 1 time interval, I'm guessing. So this is just 1 cycle. Does it matter?
Okay.
Okay. So M alpha.
10 cosine 20 pi t.
Guessing this is the message signal. So 10 cosine of 20 pi t. Right? And then dt, not just in terms of t. phase.
Oh, you didn't put it.
That's it, now we're just gonna create. What do you have?
You got sign 2019.
Okay, so. The indefinite integral would be 10 sine, 25 actually. No better than this. 25 sine of 25 t. Oh wait, but then we need to do 1/20, that's why. It's just that, because of the chain rule. This. The chain rule? Well, here we can plug this 10, right? This, and the derivative of this becomes t sine of 25 t becomes cosine of 25 t, but because of the chain rule, you have to multiply times the derivative of the inside, which is just 25. So this 25 is already out here, so they cancel out here. See it? That plus should be there around the basic. Because it doesn't, we're not mathematicians, we're engineers, right? Okay, and then what? Yeah. Is that the phase deviation? That's sine 25 t? Yeah, is that the answer? Yes, I guess. I'm gonna get this one wrong. Anyway, determine the peak frequency deviation in hertz. So I'm guessing the peak of this, what's the max of this? How do you get the max of this? How do you get the max of this? The max of the max of sine 25 t would be the derivative of this. So what's the max of, oh sorry, when is 25 cosine of 25 t gonna be equal to 2. And then you say, okay, it's when t is equal to 5, then it's supposed to 0, and whatever. The answer is this. Right here. This is the peak frequency deviation because that's the max amount that this goes through. Right?
That's chain rule again, right?
Yeah, because of the, that's the answer, right? For one reading.
Seven, 10, and
Sun put 10.
This is yeah, it'll be 10 hertz. Very good comment. Just be radians per second and then hertz. Right. Is that what you put? That's the answer. Just find the derivative of your phase deviation, frequency deviation, and you get the peak of it. I just look at the end. Now, if there was a, I don't know, like a minus something, something that you probably have to put into my laptop, then you can have to put this.
Yeah,
So 25, but in terms of hertz, like the question asks, 10 hertz. That is the peak frequency deviation in hertz, 10 hertz. This question says modulation index, which I need to find it here. The constant E is known as the modulation index, which is equal to these formulas. In this case, we have, what is it, frequency or phase? FM modulator. So our formula is KF AM over omega B omega M for a beta value, It says, what is this, 3C right now? 2C. Those watching at home. Modulation index is beta is equal to KF AM over omega M. KF being that. Right, so 2 pi. AM is the amplitude of the message signal, right? That'll be 10. Where to go? What's up there? 10? Is that right? AM would be 10? You think so? I think so too. 10, and then the frequency would be frequency of this bad boy, which is 100. Now it was 200 divided by 2 pi. Right? So it's 100, pi goes to the top. Hold on. No, it's probably 200 pi. I swear, only Euler comes up with shit like that.
Let's go to 2 pi r.
The WM? Yeah, probably 200 pi.
2 pi r. The frequency
Because the frequency is 100, so the radians per second is 200 pi.
Yeah.
These pi's cancel, these two's cancel, you're left with 110. Yeah. He's wrong.
¿Es el 10, güey?
Oh, maybe it's squared? I don't know.
Nyquist or what?
Nyquist? I don't know, because then it'll be 150.
Entonces, es el 10.
Esa es la amplitud del message signal.
No,
Over here.
Cause it's a.
Oh, wait. Okay, I see it. That's the output. This is the message signal. Oops. So, let's do this again. I was looking at the wrong one. So, it's 2 pi. The amplitude of the message signal is 10. The radians per second of the message signal is 20 pi. Pi's cancel, 2's cancel, 0's cancel, you're left with 1. Ah.
Yeah. Wait, where's KF?
KF is given, no, we solved it here.
Oh, yeah.
F was given.
Okay.
So beta equals 1. That is the modulation index, which is 1C, 2C, sorry, 2C.
And omega M is just.
The frequency of the mesh signal. This is it's 20 Hz or 10 Hz if you want to make that choose frequencies. Where? This thing?
Sorry.
Yeah.
I'm big, your biggest hater for one day.
That's true. And now we need to draw the single-sided spectrum amplitude and phase of XCT, which is up here. We haven't touched it mostly. And calculate the power. Show. Let's do that in E.
Averiguar su phase.
This thing is a phase. So that would be this thing, maybe right here. I don't know. Yeah. So that phase ET is down here. So let's see, and if it deviates from what the professor did, then we'll backtrack a bit. So we have our XCT now. Wait, I was here for this. Just look at my notes. Ah. Okay. Yeah, PT is equal to sin of 20/t. And then our XCT now is 10 cosine of 200 pi t plus that. However, what we didn't do Oh. Is this narrow band or wide band?
Why?
It is wide band because narrow band requires your B to be much, much smaller than one. Since it's one, it's wide band. There you
Ah, pero no lo veía, no entendía.
go. It's wide band. When it is wide band, you have to use what's called vessel. An approximation formula. It's narrow. It's probably in the. Yeah, for narrow band, you use this right here. Yeah, I don't know. But for this one, we use large B. We use the Bessel function. We have to look at the table. We don't have to look at the table. We could solve for it, but we'll do it for hours. So let me pull it up over here. What the Bessel table looks like. We're gonna have to print it out.
Por ahora.
¿Te encargo una?
No,
Quiero sacarlos, pero no quiero darles dinero.
no mames, esto. Las noches que voy a vivir.
Pues aquí la vending machine, ¿no?
Oh, ya, pues. Dude. Tienes Vamos, te vamos, sí. Es.
Va a estar difícil pasarla, pero pues. Well, it's for the decal. And Starbucks machine C6.
C6. Wait, what's it called again?
Double shot espresso.
Espresso.
Oh, can I get to the. Ah. Recipe.
Grace. That's the thing.
This okay. And now. Yes, we have to. Steps, 5 steps. Why do we go 5 steps? I don't know. Choose games. Oh, es this good. Man. No, el 6, C7, ¿sí hay?
If you post
Sí, bueno, eso me lo.
shit on.
Dale, gracias. This color is not in your contents. Yes. Gotcha.
I'm just tired. I took my didn't sleep already. I knocked out. And like apparently my brother asked me to call it. my car and my headphones. And I hear her say, yeah, they I was like, he lied. Didn't ask you. Exactly. And then I woke up at like 3. No, I'm lying, I woke up like around 3:45.
Like in the DM?
Yeah, no, nice. And I was like, oh shit. He took the fucking picture. And I was like, yeah, I should get it. And then I took another. Same. You know, kind of crazy. I think the only reason that I got it was because Anthony had texted me, it was like 2 hours ago. He was asking for the homework. It's like, oh shit. I think you're good.
There's turning the modulation thing on time.
Oh.
No, not that.
Not really do the. I'm gonna turn it in.
So one of the exercises to make the head order.
Hey, something's better than. Yeah, exactly. It's better.
0, 0, it's a 1.
Yeah.
What's the weight of the quizzes and homework? It's like 20%.
I should probably do them, even if he gives me something worse.
I'll just send you my code so that you can compare, not so you can copy.
I know, but I need to work on my lab. Have you done your interview?
Oh shit. 10% penalty each day? That's insane.
Still doing. Because one of the requirements is you have to be a master's. Granted, they're gonna pay for it, but like,
Okay,
I know, so I'm leaning towards it, but
which state?
Kentucky.
Oh,
Kentucky, like,
oh, I know this
like
one.
13 states are right here, and it's like on the side.
It's like right on top of the Bible Belt. Oh,
I'm picturing like
so,
we passed it up, going up to where.
it's right over here. So where is it? Oh, you can't see, that's what you meant. If you look at this picture, you can see the chef's hat, you can see the guy, the nose, the body, and he's holding.
Wow.
And this is the foot, this is the legs, this is the body, this is the head, nose, chef hat,
Yes.
and.
I can see it.
I don't have a picture of it.
Yeah, literally. So where's my note?
Oh. The Bible Belt, right here,
And why is it called the Bible Belt?
because this is where the south is the rebel. Bastards.
The title is. No jaló el vending machine. I tried it with my card.
De la cancha.
It's not like, yeah.
Ni modo,
Si quieres te puedo traer más de otra parte.
ya está, pues me hace.
Así que no hay.
Okay, now that we have our vessel proclamation formula, I think the Jade.
¿Qué están haciendo, güey?
I was teaching them how to find Kentucky on a map.
¿Por qué chingados?
Tomás,
Oh, yeah.
mira,
Eso tiene que-
it's the chef hat, the face, this is the nose, this is the body, this is the legs, this is the foot. And he's holding a piece of fried chicken. And that's Kentucky, Kentucky fried chicken. So we have the vessel values here. Our beta is exactly 1. So we have our 5 values. When we draw it, it's gonna look something like this. Gonna start at 100 hertz. So that, right? And each step is gonna be how much? 2 by? No, each step is gonna be 10 hertz. Steps of 10 hertz because the message signal is 10 hertz. Okay. So here in our Bessel signal, our Bessel table thing, we're gonna go by 10 hertz each time because our message signal is 10 hertz. So the next one's gonna be 110. Next one's gonna be 120, 130, 140. And then 100 is gonna be, we look at the n equals 0. Our 100 is gonna be 7.65. We have to multiply by our AC, our amplitude. So it's normally 0.77765. Now it's gonna be 7.65. Our 110 is our n equals 1. It's gonna be 4.4. Here. Our 120 is gonna be smaller. 1.15. Our 130 is gonna be 0.02. So it's just 0.2. Okay. It says 10. Yes. And the last is gonna be even smaller at 0.02, which is 0.002. Yeah, that's it. And what happened to my signal? Bullshit. Okay.
So if they go in steps of time to look for time samples and you multiplying also by 10.
Well, they just both happen to be 10 in this case. The amplitude is 10 and the frequency is 10 hertz. In this case, they just happen to both be 10.
So that was like 12 and you multiply it.
And now this is our base. Okay, sorry, our amplitude. Now, in order to get the base, we have to look at that, which states Jn is this over here is also 90. Something like that. One point. Is 0.2. And now we have to look at this. This is n equals 0. This is n equals 1. This is n equals 2. N equals 3. N equals 4. N equals -1. N equals 2. N equals -3. N equals -4. So now that we have our this, we're going to put the problem. One second. This right here happens to be A0 AC. A0. Okay. This is AC 1. So the ends are equal to 0 and 1 and 2 and 3 and 4. And now for the base. When n is even, like in this case right here, let's do this one here and this one here. When n is even, this is going to be equal to this. Both can be positive. I mean, I don't think you. Putting on to make the. Please. Let's Google it.
Yeah, I didn't understand that.
Yeah, we'll find out. All right, let me see. Vessel table. Basis. Analysis of the FM spectrum, the vessel functions.
Oh, with those. That's the power. No, the power. Restriction. Not to check the process. Cállate. Pues sabes, see what happens. Yeah. There you go. Man, 3, 22. All your parents.
Yeah, and then one of my girlfriend's grandma's, and then I went to her friend's. Cause he says that I'm part of his family.
Nice. How do you get the cookies too?
Oh, yeah?
Yeah.
You watch the game?
Only the Cowboys one.
American team, right? Cowboys versus the Redskins.
I think so. Not sure.
No.
So you're there, enjoying and drinking, enjoying.
Oh, yeah.
Not too much of a sports fan. But yourself.
Watch it. Yeah, like, crazy, Cowboys are beating us together.
Pretty much, it'd be a pretty cool.
45 to 10, I think. Crazy. I was gonna be a blowout. And scored.
I saw someone did it the first time. I heard like 5. Touchdowns. No, it's one of
An interception?
exception and 8 quarters.
Against something. I don't pretty know.
That's the new world record, right? Or was
Let's
it-
get that's the American way, right? Just skip it.
No,
Let's just skip it, 'cause I don't know. We did the amplitude, but we didn't do the base.
American way is shooting someone.
Well, let's not shoot Dr. Sun. But we do have our signal right here. Right? We know that it's a sinusoidal. So we can say that it's gonna be 1/2 of 10 squared, because 10 is our amplitude, which is equal to 50. This is the power of this signal. We could also square all of these values and add them all up together if you want to double check the word. Which. You wanna do that?
Wait, so why is it called the single side splicer?
Because these are only positive frequencies, as you can see.
Oh, got you.
There would be another set of them over here on the other side. And we put them on top of each other, we would have this. This is the amplitude of the outputs. And 19 joules, this is the 0, and so 7.65. 10.65 plus 1 squared plus 1 squared plus squared 50. 49 something. But yeah, basically 50. I probably made mistakes. Even though I never make mistakes, the calculator probably makes something. Determine the power at the inputs. Oh, okay, so we already got the XCT. Now we need to calculate the power at the input and the filter output. So when we put this into a filter, a low pass filter, bandpass filter, sorry. It's gonna look like. Oh yeah, we said that the filter was center frequency of 100 Hz, so the filter is gonna be right here, it's gonna be right here in the middle. And the bandwidth is gonna be 50 Hz, so it's gonna go 50 Hz across, so it's gonna go something like this. Right, 10, 20, 30, 40, half, 50, right? This. The bandpass filter is only running these through, not these.
Yeah, that's not where a little.
Bandpass, because if it was a low pass, it would be like all the way to the negative signals. Bandpass, you're not worried about the lower ones, you're not worried about the higher ones, you're worried about this side right here with the center at 100. So now we have our filter. We want to find out what the power is at the inputs and filter output. So again, we take these values, square them, add them all up together. We get, and the square is 7.611. Girl, where's the market? We get 7.65 squared plus 2 times 4.4 squared. Am I running out of room?
Right now, it's still in smooth.
Yeah. There's error cards and we can't have our next room. In fact, I'm recording it through Zoom, so I need to see. 7.65 squared plus 2 times 4.4 squared. Plus 2 times. Where is? That's the power at the inputs, no, that's the power at the outputs. This is the power at the output. Right?
I just forgot the output again.
Well, it said, it was given in the problem, at the beginning of the problem, that the center frequency was 100 and the bandwidth is 50, sorry, 50. So it's just 25 this way, 25 that way, centered at 100. And it's 49.94. That's what I believe. Guessing most of the power is gonna go through because these are very tiny right here. You know, so they're not gonna be that much of an effect on the power of the signal after it's been filtered. So I got 49.91. And the original power was 50 watts, so the filter dissipated 60 milliwatts. That's E. At least that's what I can think.
Is the month those times 4?
Yes, because there's a 7.65 and there's 2 4.4s. There's 2 1. Yeah, this way. Any questions? Any questions? Actually, I don't know too much about that. But
Oh, I see.
Yeah, ¿alguna pregunta? No? I don't know very much what's going on either, but hopefully we know it now. I'm guessing we need to write down these formulas in our formula sheets. We have our KF. Is equal to 2 pi FD. FD happens to be the frequency deviation. This is the. I don't know. Figure it out. Oh, this is very important. There's two of them. B beta is equal to AF AM over omega M, or this is for FM. And for the other one, AM for PM. APAN for PM. That's the case. Okay. Sounds right. Okay. The other formulas that we missed. Is that
Here, yeah, party,
right?
pero mejor escribes del lado, ¿no? Que del otro lado, que porque no la vean.
No se ve. A los demás no le vean.
Digo, no, o sea, como quiera, no importa. Lo podemos escribir o mandar una foto después.
Creo que se ven. Zero, M alpha, E alpha, square. Okay. So, no questions? Raise this and go ahead. A wide band because the beta value was much greater than 1. Narrow band if it was much smaller. Much smaller than that.
Why is that? Because it is one, or like, what's the?
If it's wide, it's right here. Narrow band modulation requires beta to be much less than 1. So the Bessel table accounts for beta values as low as lowest 0.1. So I'm guessing 0.01 is part of the cutoff. I don't know. You know what I mean?
Yeah.
Again, the Bessel table accounts for values as low as beta equals 0.1.
O sea, que usted, tipo,
No, he wants us to print it out.
so does that count for our like limit of sheets or not?
We have. Yes, we have the Bessel table. What do you want, orange? You need to take a Bessel table. We need to take our cheat sheets. We can take an integration table. I don't know if we need the transform, but I'm pretty sure we're allowed a Fourier table. And we're also allowed trig identities table. It's all we're allowed to perform. Fine, okay.
Partner,
Hopefully.
partner with the, is he gonna like?
No.
That's gonna be crazy.
Yes, no emocionaste por nada, por eso.
Okay,
It's
yeah.
A delta modulator has a message signal. Shouldn't be doing it, so it must be very unusual.
Yeah.
Good if I don't make it private.
That's.
But now I kind of wanna go like, somebody looking it up like, oh, how do I do this?
Let's put the answers in, in addition.
Hacer de mano.
They'll get,
Me quedé todo buscando para arriba.
I just gotta stretch me. Just gotta stretching, you can answer.
MT is equal
He doesn't
to
even play.
the cosine
Last time we had some.
of.
So what if,
Brady, so that's.
yeah, probably.
That's 10 hertz.
Is this?
Yeah, number 3. This message signal is 10 hertz. What?
What?
Your feet.
Oh,
Quiet.
nothing's wrong with my feet. Okay, we know this is 10 hertz. Determine the minimum sampling frequency required to prevent slope overload, assuming that the impulse weights, what's that, delta naught, are 0.1 time. So, so there's gonna be a slope, there's gonna be a signal that's like, right? Now, our delta modulation is gonna just be little tiny steps over time. It's gonna be little tiny steps, right? If we, if it's not steep enough, we're gonna miss out on a lot of the signal. See what I mean?
Isn't it just one?
No te me adelantes. If our, what's the word? Sampling frequency is too small, we're not gonna get the entire signal. We can reconstruct it, that's the Nyquist rate, we can reconstruct the signal, but we'll lose a lot of information out. So in this case, our slope is, or the times t, the height is 0, let's zoom in a little bit. It's t and the height is 0.1 pi. Okay, that's the slope. Right here. Right? So we need to find a t value that's small enough so that it has time to reconstruct the signal. As the signal can play out. We don't want to be sampling too slow in order for. You don't want to be sampling too slow or else you'll get a lot of this missing. Therefore, we have our formula here that he gave us. 0.1 I over t has to be greater than or equal to dmt derivative of the message signal with respect to time. Does that make sense? It's the slope. Okay. This slope, which is rise over run, has to be greater than or equal to the derivative of the message signal with respect to time. The message signal is up there. All we have to do is find a derivative of that, which is gonna be 400 pi negative sign 2022, right? Change. Wait, those 20 is 400. So this is that right here. So you can replace this with 0.1.
The derivative of the functional function? Did you just do the derivative of the original function?
The message signal. The derivative of the message signal is this right here. Oh yeah, I combined the 2 pi
Oh, I
term and it's 20 pi.
Yeah, yeah, okay.
That's just how the problem is.
I can see because of your face.
Now, we wanted the slope of this, the slope will be at its highest. This. It's like. Right here. Right? So it's gonna, the slope will be, the highest will be right there, 405. The slope right here at the highest point. Make sense? The highest point of, the fastest slope of this table right here is gonna be 405. Yes or no? Yes, that makes sense?
Highest,
The maximum slope, the highest this slope is ever gonna be. Is 405. Right, because right here, the slope is 0. Right here, the slope is the maximum it's gonna be. And that's when it crosses the origin. When does this cross the origin? At, let's say t equals 0. Right? Sine of 0. 0. And we'll ignore that. Well, this right here is when it's gonna be the highest point. So that then that happens to be 405. That's how fast it's changing. I think this is gonna be this is gonna be at like 90 or something. Anyway, that's gonna be equal to 1, 2. Yeah. Okay,
where's the formation?
that is the derivative of this right here.
Oh, okay.
So now we have. This is greater than or equal to 400 pi. We can divide by pi on both sides. We can multiply by 10 both sides, we're left with 1 over t. Is greater than or equal to 4,000 samples per second. So 1 over t, which is the rate of which these happen, has to be bigger than 4,000. Or if you want to look at it, this has to be 1 over 4,000. Okay. You understand? That's to be 40,000th of a second in order to be able to cover our signal decently. Now, does the minimum sampling rate required in problem A, which is here, satisfy the Nyquist rate? The Nyquist rate is twice as much frequency as it is inside of the cosine. So the Nyquist rate is equal to 20 hertz, 20 samples per second. And we have 4,000, so yeah, it satisfies it. The higher you are from the Nyquist, the better the signal will be. So the problem, no credit without justification. Yes. Nyquist rate. The A era the minimum sampling frequency, which is 40,000 samples per second.
And then that's the minimum something.
It does satisfy it because the 4,000 is a lot bigger than 2. Now, if this signal was like a little bit less ample, yeah, would probably be easier. If this was smaller, the derivative would be smaller. There you go. The derivative would be smaller, so you probably can get away with less samples per second. But in this particular signal, 4,000 is the recommended minimum 7 with these weights. Four. Any questions on 3? Great. Oh, you know why I was confused? Because this is local, right? And I was looking for. So I should have found the cosine. Yeah, whatever. How about uh, delta over t has to be greater than the derivative of the message signal with respect to time. Grace is so good. Number 4. For the message signal, mt equals negative ut and unmodulated carrier cosine of omega ct. Now the output of the phase modulator with mt is pi over 2. For the message signal, gonna be equal to negative ut. And you're gonna have to bear with me because you didn't do this in class, we ran out of time, that's as per usual. Carrier. Cosine. And okay, so it goes pi over 2. All right, that's all we need to know. Output of the phase modulator. Well, when you do when you modulate it, yes, there's a message signal, right? That goes in. This is a modulator, and out comes is the carrier signal. I guess it's like with a X. We have a carrier, we have our empty, and now we have the output, which would be, I guess, CT, like that, right? So draw the output. The carrier is, that's cosine wave. The message signal is negative ut, which looks like that. No, that's negative t. Sorry, it's like this. This is right? Because if it was negative t here, that's when it would be over here. But since it's negative over here, it would be down here, negative value, negative amplitude. So the output here just be their products. Right. Now the output is gonna look like this. When you have your cosine and you multiply by -1, it's just gonna go like this. Now it KPs. KPs. KP extra information. That makes sense. Not sure.
ni eso, el Slider ahorita no.
What?
Y el Slider.
I was looking for it. Should I learn it? It's the key. Is it the base? Something.
What is one? No, the.
I look at base modulation. Um, Didn't end up using KP.
KP is the constant of proportionality. The deviation sensitivity.
Well, I think it's right. Anybody disagree with that being the answer? Jumps. It's over because he wants to put this -1.
So
Also, would this be 0? Right here, it's all zeros.
yeah,
Like that. Yeah. That's probably it. Oh, because the signal, the message signal starts at 0. So everything before would be at 0 here, and then 0 times anything is 0.
Todo otro vale.
I think so. Right? Makes sense. I think it makes sense. I don't know what the KP is for. Next question. For the message signal, MT equals probably for this. MT equals -VT and unmodulated carrier shown above where WC equals 25. Draw the output frequency modulator with MT F equals 10. What? Okay, so this carrier signal is now gonna be, oh, let's do it in blue. So this is now gonna be cosine of 25. And after B. Draw the output of the frequency modulator with MT. Constant. What the heck is it?
Frequency deviation constant.
Frequency deviation constant.
Digo que lo estamos viendo en este, güey. Hay muchos. Vale. Pero
Oh, it hurts pretty little too. ¿Cómo se llama ese?
este me está retando, cagando, vamos.
Es el Frequency Deviation Constant.
¿Cómo se llama el power division?
It's like one. The angle relation. Esa página. Es la que estaba viendo hace ratito.
Output of this modulator within this.
Tenemos over a D. Hace ratito. Oh no, it gave us a D.
Is there a slide that says phase deviation of PM?
Which. Is it space modulation?
Go back to the one. That's the name. That one?
Phase modulator. Deviation constant. So,
So you multiply for one.
I guess so. Your 5T, there's a 5T gonna be equal to, there's a phase deviation. Or the output of phase modulator. Well, it said that it was just gonna be a bunch of drawings, didn't he?
I think this is an example, I saw an example, if you scroll down on the PowerPoint. You good? That one, right? That's
So this is cosine. This is cosine plus APMT.
oh yeah, that's what you do.
Hmm. Output of phase modulator. Okay.
Would it be?
Backwards. So it comes over upside down. Yeah. Well. Where's this? Look at that. Draw the output of the big modulations right here. So this is gonna be just. The regular signal, which is just gonna be a T. Number 290. Australia. Wait. Two. Unmodulated carriers.
You do have to multiply it to the MT.
Just. Negative five. Which different?
So you wanna shift the cosine wave?
Yeah. Negative 5
I'm looking at this one.
example, right?
Yeah, like this. It says like
Yeah.
you have a EMT, which is the step. And we have the cosine,
You got it?
then you add those cosine minus T plus EMT. I don't know what that is.
That's a different one, I think. That's the frequency. Deviation. Right? Yeah.
I think so.
So
It's up here. I just saw it.
let's look up the KFKT though. Oh,
Well. I think it's gonna be. Something like this. Maybe regular, and as soon as it hits one, it's gonna be like. Best. Something like that. Sonidos acá, aquí dice. Frequency modulated carrier, that's this one. Last one. And it's asking us for frequency, I'll put a frequency modulator.
Here, I don't know if it's still.
That's what I'm looking for.
oh. It's not like 5 times FD, no?
He has it over there, I think.
Oh,
Yeah,
2 pi times FD, what's 2 pi times 10? 20 pi,
Yeah.
which is KP 20 pi. But that's not pi over 2.
yeah. IFD.
I think it only goes faster like that.
Oh, that's the question, so like, yeah, I'll put the frequency modulator.
Oh, really?
Yeah. I think for AV, I thought it was just gonna be
It's also wrong.
probably wrong, yeah. Well, no,
No, because I was asking for
Yeah.
phase.
Yeah, that's phase, and then that's the other one.
Yeah, you could do frequency, yeah.
But I feel like the B will be like sharper,
Yeah.
little less,
Narrower.
yeah, narrow side, yes. Cause it's not pi over 2 now, it's 20 pi.
yeah, like stupid.
Yeah, yeah.
It's probably gonna be.
Yeah.
It's probably something like that.
Yeah.
I don't know, YouTube, I'm sorry. Don't hit the dislike button.
Yeah, it's so hard.
Random processes. Woo. A is 1 and B is uniform distributed between 2 and 6. You're the fifth. Yeah, we kind of wrote it down. We have to draw it out, something like this. It's between 2 and 6, right?
It's not syncing.
It's uniform between 2 and 6, it's gonna look something like this. Right? It's not a normal distribution like a bell curve or anything like that, it's evenly distributed. Right? So the size here is 4, right? Now, what is the maximum probability? The probability?
One.
No, 1, the maximum probability.
Yeah, one.
100%, right?
Yeah,
Oh,
yeah,
So
yeah.
the area of this must equal 1%. So if this is 4, this one has to be 1/4. Right? So that the uniform distribution is 1. Distribution of the probability coming 1. That's it. That's the PDF. PDF stands for. I wrote it down. Probability density function. Yeah. Probability density function. All right. Now for sketch 3 sample functions, that he said it was like, I don't know what he meant by that. The way he said it. The way he drew it, apparently. He said that these were acceptable answers, I don't know why or how. But he said a 3 and a line. And then a 4. And a line. And then he said again a 3. Line. That's literally the answers he gave us.
Did you see it?
I don't know what that means.
It's the probability like.
Oh, yeah.
So I'm guessing we fall somewhere here, 3, let's say fall on 3. So you start at 3 and then the next one, I guess, goes higher, 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 because you're falling into 2 and 6. All I know is that I wouldn't put a 1 or a 7 here, except outside of the bounds. So just put something between 2 and 6. Or
Y una línea there.
yeah, that's not all I would do, honestly. Yeah, so maybe because there's no negative numbers, it's not going down, it's only going up, because the only possibilities are between 2 and 6. Trying to read his mind, everything. Find the expected value of x.
It's still 5.
X equals 1, huh?
It's still 5.
Yeah, 5c. So, what's the formula? AT plus B. The formula is AT plus B. We said A was 1, it was given. E is between 2 and 6. Okay. So we have T plus some number B. So when T equals 1. Find the expected value of x when t equals 1. Between. What's the average here? 5. Because the average is 4. So maybe this would be 4 is equal to 5. So we and he also said that when t equals 0, it would be equal to 4. I wrote it down, that's what he said.
Yeah, I know.
So if the average of these values is 4, I'm guessing that's what you would add here for this B, which is between 2 and 6.
So what is
B is the range of this right here. So when you start at, when you start at 0, right here, the average would be probably about 4. And then just keeps going up. Oh. That's that. That's literally what he wrote down. Just on Tuesday. Multiple choice. Woo! Phase deviation constant KP equals -5 for phase modulation. The carrier frequency is 100 megahertz. What is the phase modulator output for the message signal MT? Oh, he wrote all the answers. Oh, nice of him. All right.
And he was trying to make it hard for us. Couldn't like bold that. Highlight it.
I was gonna go erase it. I was like, look at it, look at it here. What are you doing there? So, phase modulator carrier frequency is 100 megahertz.
Quiero que me
Why is she-
ustedes.
Oh, right there.
Correct. Why le borras los?
I guess it just says C.
Would it be C? Maybe he like it is type.
Imagine it.
Why would you do this?
I'm gonna game with my television. This is, I'm gonna say this is preset 1. Idiot. Oh, okay.
Te pegan un sueño.
Ya me lo acabo, ya me lo acabo. ¿Qué me puedes?
Like 30 probably.
I mean, it's-
What happened to the trash can?
6 minus 20.
It's outside.
It's outside. Like 14. I don't know, man.
You're down for the laboratorio, man.
Chingarle.
I know he ain't talking to me.
You're in my team, what do you mean?
Okay. Well, camera number 2.
¿Me puedo ver o no?
No, vamos a ver, vamos a ver.
No quiero estar.
What is the phase modulated output for the message signal, blah, blah, blah. Well, we have the message signal here, the frequency is 100 megahertz. We have to multiply the carrier frequency times this, maybe? And that's how we get this?
Why the negative 20? Oh, because of the AP?
Let's try it.
I hate you.
That's your weakness.
It's the first stuff.
Yeah.
How dare you? I was trying to get your attention.
Phase modulation, phase modulation.
What's FC?
X.
The carrier.
Yeah.
Okay, yeah, that makes sense.
Sorry. Yes, drum.
Cause it says on the book. you know,
Oh.
With these definitions, the phase modulator output is XC of T equals AC cosine 2 pi S.
Times in representing, it's the carrier signal is 100 megahertz. So I'm guessing it's like cosine of 200 times 10 to the 6. You multiply these two together maybe and you get those.
Phil, what you doing?
Multiply.
Oh, it has to be pi though. Acuérdate porque si no tiene pi, entonces no lo subes a hertz.
No tiene pi.
Sí, güey, pero luego no lo cambias en hertz.
No sé.
¿Sí me entiendes?
Bueno, it is gonna be a cosine. This cosine is cosine. I'm guessing the sums are chingos, minus 10 is still chingos. Right? Oh, so that's 100 times 10 to the 6
Oh, negative pi.
times 2 pi. Right? But minus that because it's minus 20. So. Algo así. Similar. Similar. Alright. Wolfram Alpha. Alright, perfect. I like Wolfram Alpha better. For this.
So did you show the steps?
Huh?
Or what come out? Did you show the steps?
Maybe. I don't think so actually. Let's see. Simple.
Siempre lo hacen y todo esto.
Almost.
Pay for it.
Yeah.
Yeah. So it's just gonna be 20 cosine of 10.
Oh, it wasn't told me that simple. Oh, you have to pay for it now? Yeah. Well, if you want.
Then you
That's-
buy, just figure it out. Does it, the thing that have.
I don't know, man, I
It
got
does
C,
apply.
so I'm good.
It does have pi?
Nice. Another one is just cosine of 100. 1, 2, 3, 1, 2, 3. Times 2 pi. T. Algo así. Solution. That's literally what I just typed in.
Press subtract.
Wait, but why are you multiplying?
Yeah.
20 pi, where's
Oh.
where's the,
AP or whatever,
yeah,
this thing, well, I guess negative pi. I, where's that come from?
you wanted the answer or what? Let me know when you're ready for the
Oh
answer.
my God.
Fine, tell me this. Well.
Look here, I'll show you. That's all I know.
Oh, KPMT, oh.
Yeah.
Okay, fine.
If you want choice to say, what? If you can multiple choice, maybe the same.
Oh no.
Probably.
So
Then-
At least so similar.
the answer is the amplitude, which is AC, it's in terms of the amplitudes already. And then it's cosine of that, which is 200. Yeah. It's 2 pi
So it's
times 100 mega. 100 mega. And then you subtract this because the KP is negative pi, which makes it inverted. So then it's just 20 cosine of 10 t I, but the question doesn't say I, so it's just.
Wait, what?
Because the KP is negative pi.
But you
You
still
need
have
pi.
pi, cause KP is negative
two
pi.
pi, yeah.
So you're multiplying the 20.
2 pi F, 2 pi F.
There.
Yeah, there.
That's because the formula is
AC cosine,
of the carrier of ACT.
yeah, or 2 pi times the carrier frequency.
2 I FC. Oh, FC,
Yeah, FC,
I guess because it's not an angular,
yeah,
it's FC,
T plus KP
KP,
and T.
and T. So this is the formula right here.
You got a parentheses, put one more parentheses.
So the formula says, that's the amplitude, they say, this is the carrier signal, which is 100 megahertz. KP is our negative pi, which translates everything into, it flips it and makes it destructive, and that's why it's negative. And it's 25, that's the message signal. That's where the answer is C. Barely see that on in the video. There's 3 people, they probably just recording.
Not even,
And that's why the answer for the first multiple choice is C.
it's like, damn, it's already. But it's 6.
Studying all night.
It's gonna get on the M or.
Alright, next question. We wanna get out of here, right?
Yeah.
Frequency deviation, is it the same thing? Well, there's a frequency deviation constant, not the phase deviation constant. Is 1 for FM. The carrier frequency is 100 megahertz, what's the frequency? Let's write this down first. More formulations.
Yeah,
Yes, ace.
oh, by the way, you raised the line, so I don't think they can see that.
Oh, yeah, I'll bring it up later. See,
Oh, you raised the line, man.
We're lining this.
and
We're lining this.
there. And this is equal to what?
XCT,
X, C, N.
no, on here. I guess, I don't know, it says XC, but you know, put your
Oh,
little
okay.
N in there.
Well, output of the phase modulator, I guess, would be phase modulation. Alright. Erase this. Should've kept that. Oh, well.
Say,
Yeah, but.
what is it?
Sure. It's gross. That sounds like, yeah,
it's a group.
Okay.
one has one, but like, one is another.
So the carrier frequency. is equal to again 100 megahertz, so cosine of 2 pi times 100 megahertz.
Oh, did she?
Doesn't say property.
Puede.
She's a bullet. Just a minute.
Ah, okay.
Micromanaging?
Message signal
You
is
saying that
n cosine of 10 t.
Again for them.
Again without a pi, for some reason. What is the frequency modulator output? What's the formula that says there? We'll see it. You said you had the formula there.
Okay. It's XC of T
X C O T
equal to A C
C and two
cosine
cosine
and then bracket or parentheses 2 pi FC
2 pi F C
T plus
plus
2 pi F.
T0.
I guess, and then M alpha.
M alpha. No,
Yeah.
when I use the message signal.
Alpha?
Yeah.
Yeah, I don't know.
And then close.
Yeah.
So. Let's see what this integral is. What's the integral of this cosine, this message signal right here? I think it's just gonna be sine.
What, sine 10t?
And
What is?
that. Yeah. So. The answer is gonna be AC cosine of pi 100 mega. Plus 2 pi, what's the RP is 1, stays the same. And then sine of 10t. So. Is that it?
Yeah, that's it.
Aha!
Wow.
Formula wins, okay, easy. Wow, so this is for FM,
So helpful.
that's for FM. You want to get clap the sheets? Whoa, so if it's an easy clap, it's an easy win, okay.
Yeah, for 4 day.
So is that, this is for FM or what?
Yeah.
FE, frequency deviation,
Wait, what?
it says frequency deviation
Yeah.
constant, I don't know,
FT is, yeah, frequency deviation.
frequency, it says frequency modulator at the bottom,
Yes,
for
yeah.
FM. X T is equal to AC. Well, I'm just passing it. I'm telling you, facts of life. 2 pi FCT. Plus 2 pi FB. Message signal. Boom. Who's that? Did you get that?
Copy.
We?
Oh.
I saw it.
There's a formula that Nicole was Nicole's very nice for vertical. So this formula right here, we plugged it in, the integral of our message signal is just sine of 10t, and that's where the answer is. E.
All that calculus comment.
If I was to do integration by parts, I'd die.
No.
I would die. I'm barely even, what's the word? Literate in U substitution. It's like as high as I'm getting.
I remember in calculus 2 one time they gave me a problem that it did like 3 iterations, 3 or 4 for iteration by parts. I'm like,
Fuck that. It was a, oh yeah, the exam will be just one question.
yeah. Then no, you miss one negative and it's fucking over.
Yeah. So the next one says, the carrier, for problems 8 through 10, which is these things. A narrow band tone modulation for FM is given as this. This is the narrowband especially.
And so yesterday.
The carrier signal, lo usa esta.
For you.
Yeah.
Ay, good.
No.
I need a pointer now. The carrier is 20. 20 cosine of
Recorded too, so
100 megahertz. And the frequency deviation constant is FP1, the message signal is 20. Sorry, cosine of 100 hertz. What is the frequency modulator output at 100 plus 5 hertz for the message signal?
Bam.
Vamos a la 8 and they're like.
Zero.
They're like,
It's supposed to be 0.
wow.
What did he say?
We're on 8.
Oh.
Yeah.
Okay. Well, let's use a formula. Okay. Is this a formula again? FM? Yeah, this is our FM. So our FB is 1. Again. Our FB is 1. Our message signal is cosine of 200 pi t, so it's gonna be what's the angle of that? 1 over 200 pi?
Is it sin problemas with this time?
Maybe, I don't know, I'm gonna try. 1 over 200 pi.
What's the formula for power? Could you see that one? And then
I think we have to find this,
let's find work.
Let's do
the
this
signal.
Yeah,
Yeah, we have to find the signal first and then.
and we'll probably do it in the face diagram. And this is gonna be sine again. 200 pi t, like that. That's this. And then. AC is 20. Right? Frequency deviation constant is 1. So, okay, what is the power at 105 hertz? Why is it 100 mega plus 5?
I was like, maybe.
He hates us. The 100 mega.
Again, 5 maybe, T.
On the T. It's too algebra, that sounds. Science out of my cosine, it's really.
Oh, yeah, I with that.
What is the power? Well, simple left. Simple left.
No.
Simple as gonna be like what?
That's something.
You're using the wrong one. For real. A narrowband tone modulation, that's part of what it is. Narrowband tone modulation. That's what it is. Go ahead,
Oh, look,
suppose empty and simple tone, okay,
tone modulation again,
see,
that is the key.
for narrowband tone
What's your age
modulation.
range? Oh,
It's a third.
Okay.
El narrowband, aquí,
Okay,
y luego le doy para abajo.
xt equals AWT cosine. Como lo viste así. W equals a pi t. Yeah.
It's a narrowband application o angular modulation, pero no sabemos, pero tiene tone modulation.
Well, the answer is 0.
Yeah.
Skip to the answer.
Lo otro, güey.
Narrowband tone modulation. We don't have a theta value. We can calculate theta maybe.
Doesn't maybe just leave it at beta?
It's a peso, it's a peso.
can calculate beta, is it space modulation? Frequency deviation. So this one, yeah. So our beta. Races. Okay, let's say carrier is cosine of
That's not
200. Six. IT is the carrier, the message signal is cosine, it's cosine of 200 IT is the message signal.
That cosine of it.
That's right, you give us close. So we can calculate A or beta by using the formula AF. And then FD. And FD is actually there. So A and then goes to FD. FD is 1, so AF is 2 pi. And then AM is the amplitude of the what? Amplitude of the message signal, just 1.
Yeah, it's fine.
And then the frequency is 200. Or actually 100. No, it's 200 pi.
Right.
And this cancels, that 100. That is much smaller than 1. So it's narrow band modulation. And it was already given to us, we didn't have to do that. Hour. Well,
You have to use the vessel table again?
no, because it's narrow band. That's what's for light band. Well, let's use this formula right here. They must have given it to us for a reason, right? And then they just put it there for no reason. True. Can you see what I'm doing? You cannot see what I'm doing.
Yeah, these two.
You guys need to speak up.
There's no one there. It's on. There's just
No, they're still there.
Sorry, I went to the restroom, so I didn't see
Oh.
that it wasn't turned.
I wanna hear you pooping. What?
Ace.
The turkey came out.
But. This is the formula. We already knew beta was very small. We already knew beta was very small. That's why I raised it.
Shit.
Let's write down the formula as it is given to us
Did you write
in the problem.
You got it? Well, I didn't even write anything,
No,
cause it was wrong, no?
No, I don't.
What I had written down was that I calculated beta by using AF, AM, and WN. But we already knew beta was very small because the problem says narrow band population. So we have the formula, which is AC cosine of omega C minus AC B beta. Which those look at the top one, I'll look at the bottom. Do we want to look at the top or the bottom? It's simplified. Oh, I want to simplify. It's longer, but anyway, let's try. AC beta over 2 cosine of omega C, which comes there, minus omega m T plus AC beta over 2 cosine of C minus omega m. Okay, what does this mean?
You got me there, son.
Will these two cancel out?
Well, we did, if it's canceled,
Yes, it should.
No, this is got a plus and a minus in there,
yeah.
in the cosine.
Oh, okay, I see it. Yeah, alright.
It was
Are you gonna sit on this shirt?
Oh,
No,
no.
okay.
So we know the amplitude of our carrier signal is 20. Cosine of the carrier signal, which is 200 million. Oh, 100 million. Yeah, 100 million. Alright, I guess 200. 619. Minus AC carrier signal is 1 million. This is tiny, but we can, it was 1/100, right?
Well, no,
Yeah.
but okay, look.
Over 2. Okay, and then the carrier frequency was 200 million. Minus.
About double time.
Oh,
Yeah, you forgot coastline.
no, it's just, oh, I see.
Thank you.
Thank you. Good job, that's extra credit for everyone.
Yes.
206, IT minus message 200. IT. Plus. And again, 1/100/2. Cosine, the same shit, but instead it's plus. Okay. Now we got the power.
Awesome.
No, really, it's.
What's, okay, that's what, 2/100, 20/100, or 2/10, divided by,
This.
yeah.
here, This
10 over
cancels
100.
1. 1. And then 10 times 100 is just 1/10, so this is all 1/10, right?
Oh, but you forgot a 50.
Right.
Oh, wait.
This is equal to 1/10, right?
Yeah.
No, yes, it's divided by 2.
Times divided by 2 is 10,
Yeah.
10 divided by 100 is 1/10.
But it's not divided by 50.
Huh?
Which is
One, because you said 1/10, right? So don't you have to divide 2 to everything?
And over here,
No, like 1/10. Would it be 1/5?
Wait, why?
That's 100 divided by 2 is 50. Or am I thinking that wrong?
oh well, it's 100 times 20,
Oh,
which is 1/5, but then divided by 2 is 1/10. What's the power of this?
First of all, you get squares instead of cosines.
that's true.
Yeah, that is difficult.
We're gonna put
Only you did.
Just, I know the
Okay.
Is this the answer?
Oh, we have to take into account 100 and plus 5. That's the key here.
What's the answer to that?
Answer is.
0.5. It's not even there.
That's 0.
Chiquitito. Well, I'm guessing it's about 0.
Yeah.
But yeah.
It's a huge, it's really tiny number, so it's very 0. This one.
No, check.
Huh?
Pick it up on check.
I don't have checks. I use.
Oh, it's all up here.
Yeah.
For you.
Exactly. Well. That's it.
I just don't have it because I can afford it.
100 milligrams plus 5.
Maybe 0 is not a plan. Plus 1.
Well, there's 3 terms. This one is. This is what? 200 million minus 200 is like 199. This is 200, but there's like 2 over here. This is 200 million. Oh. Um. We could draw the diagram. This one's gonna end up being all the way over here. At 100 mega. So 10, right? Oh, here's gonna be. And then yeah, it's gonna be 100 mega. These get complicated. There's gonna be 100 plus 100 mega plus 100 is gonna be here. That's this one.
Which one? Oh, no, 110.
110.
What amplitude?
No, we have the 110, so we want to.
Oh.
No, it will also be 20, maybe. Like that. Minus 100. And then over here, same shit. 20 minutes, like 86. So then we add them all together, we should get 0. That's 100, that's 100. Let's do it, look at it. Make it equal to 0. 1/20
Lo restaste, okay, güey.
squared.
You actually, you actually like subtract them. You can actually subtract them.
Yes, because there's no t in here, so maybe this is not t squared.
So it's the same, so you can probably subtract. No, is there no T?
Yeah, there was no t. There's no t's in here, so yeah, you can probably subtract them and then
Oh,
you end
yeah,
up with
it's
a,
a T, does it?
and then you end up with a spectrum that looks like this. So then plus minus 2 plus 10 squared.
Probably, oh.
But you are right here, the wedge is that, if you look right here, there's nothing there, so maybe that's why it's 0. At 100 million plus 5 hertz, there's nothing there, so that's probably why it's a 0. It could be that easy. It's like you said, there's nothing here at 100 plus 5.
I think it might be, cause for 9 of 10,
Yeah,
the
or-
answer is 200 and 100 mega. Then we just do like 2 times 10 squared. And that's 200. So maybe it's just power and.
yeah. Well, let's do the next one, and it'll probably be the same thing. But the thing that's different here is that this 100 is gonna be one step above this one. So there will be a power there, it's gonna be tiny. So let's see. Erase. You ready? No? No questions?
Yeah.
Let's focus on that.
Let's focus on the ones that we can answer. Yes, true. And well, let's do this one because we already invested in it. I shouldn't have erased it. Oh well.
No te right?
What else? Undo. Well, I can just remember that it was right here was 10, 1/20th, right? 1/20th. And over here again was 1/20th. And which is not to scale for sure. Okay, and this actually right here is 100 mega plus 100, right? So the power right here would be that quantity squared, which is 1/20 squared.
Point of adding 100 or 5 to 100 mega.
That's true. Measure what you do.
You have the formula for GP? That's KF or
Oh,
something.
well, KP is here. When it comes to me, it's given to us. KP is used,
So far it's been given to us.
yeah. Well, the power that I'm getting is 2.5 milli, not that.
They fuck it in. The same.
Yeah, let's just go to the one that we can know. We're at 100 meg, it's probably B 200, why is it 200? Because it's 10 squared plus 10 squared, I guess. That's why it's 200. Let me see. Well, this is for 9, for 10. For 10, we're doing 10 squared plus 10 squared, that's 200, and that's why it's B, you guys see? Okay, next. Columns 11 to 14 have a continuous data signal is quantized and transmitted using a PCM. Base carrier modulation output. If each data sample at the receiving end of the system must be known to within 1% of the peak-to-peak full-scale value, how many binary symbols must each transmitted digital word contain? That's so it's 1%, right? That means it must be accurate to 100. Must be accurate to about 100 of accuracy. So there must be right here, from here to here, there must be 100 points. Okay, how many digits? How many digits in binary do you need to make 100? You have for 1 you have 2, for 2 you have 4, 3 you have 8, 16, 32, 64, 128. So 7. Oh. The answer is 6.
Sorry, so one, you got from one. Is it one?
Yeah, no, it's supposed to be half. So the fact that it's within 1% means that right here could be 1/50th to 0. There's 50 steps right here, and then that would be within 1%, something like that. We're gonna here somewhere. Pulse code modulation, that's what the CM means, pulse code modulation. See, when it was 0.005 error, it was 100 levels. If we were to double this, it would be 0.01 and it would be 50 levels. That's why it's 60. Yeah.
So where the fuck is the 50? Or
So there must be at least 50 levels in between each point. So this point right here would end up right there. Okay?
yeah.
So the fact that there's 50 different levels means that it's either too much or too little. So you double it, the level, or yeah, you double it to get your percent accuracy. And then, yeah. So trust, it's 50. How I got this.
It's 6.
Let's say,
Oh.
yeah.
I don't
So
So at one it'll be 4.
Yeah, just
or what?
sure.
At 1 it will be 4, and then 2 at 8, like just doubling every
I guess so,
every
yeah.
bit or whatever.
Like if you have 0.01, that means there's 50 levels. And the 50 levels is where you get the 6 from, 6 digits of binary. Pues sí, pues, si yo quieres transmitir nada, pues no mandan nada. Yeah, and this I'm sure I'm not explain it, but. You would think there's 100 levels, but there's half of them, you know what I mean?
Don't you start the count at 0? So it'd be. Right now.
There's 50 levels. And the maximum amount of wrongness you can have is like
1%.
1%. And you have an infinitesimal amount less than 150, you would be at 0, and that would be very long, and good, bro. Get the inverse of this. That's 100 divided by 2. Got it? Got it.
Thank you.
Inverse of the error divided by 2. That is your number of levels.
Okay, but how would you, once you know your levels, how would you know to pick 6?
So you have 50 levels, you need at least 6 binary digits.
Nice.
Sorry, that was louder than I thought. So for
So that's your levels, then what?
It's 6
I try to really understand. That's kind of because I.
For the question.
Plus or minus 1%.
For pulse code modulation, you get your errors, you get the inverse of the errors,
Check
divided by 2, and that'll equal your levels. And then from your levels, check minimum binary. Okay,
So why is it inverse though?
because 0.01 error or 1% error, the inverse is 100, and that less.
Oh shit,
So you
okay,
think
I
it's
got you.
50, and we're using 64, because it's like.
Yeah.
Because 128 would be for.
If you wanted to get like 0.5% error, you need 100 levels, and that's what you can use segments. Oh, you have 28 bits to transmit. That's about the signal. But anyway.
Okay, 64 close to the 100 or 128 close to.
Well, you don't wanna go below,
You need at least.
yeah, you need at least that much.
Yeah.
So you wanna go above 50 levels, 6. If it was like 40 levels, I would still go with 6. Assume that the message signal is speech per telephone, which has a bandwidth of good. That wasn't me.
No.
I hit it over here, not over here.
Yeah.
Assume that the message signal is speech per telephone, which has a bandwidth of 4 kilohertz. What is the minimum sampling rate per second without aliasing effects? Questions? Any guesses?
Yeah.
Minimum sampling rate per second,
Minimum sampling rate, I just do my quiz, that's just me though.
which is
The 8.
You know,
That's the only thing I remember from fucking, what's it called? Yeah. Like this.
So when you have a bandwidth of 4 kilohertz and you wanna get no aliasing, the minimum sampling rate will be the Nyquist rate, which is twice as much as the bandwidth, which is 8 kilohertz. So 8,000 samples per second. Estimate the bandwidth of the resulting PCM signal.
it's twice the what? The something rate, right?
Yeah.
The bandwidth of the resulting PCM signal. Well, we have 7 bits. 7 bits times 8, it's 56. Oh no, 48. Wait, what?
And then the 1% error or point.
Yeah, that's the 7 bits. That's what, sorry, 6 bits.
Yeah.
Not 7. I said,
Yeah,
I think it's 7. 7 times 8 is 48. That's why it's 48.
7 to 6.
Oh.
It's 48.
So we messed up on the binary count, whatever, we messed up 4 problems, basically.
Yeah, basically, if you say 7, then you
Yeah.
you're gonna be for the next few.
Oh shit. I didn't even realize.
Actually, no, 14.
Yeah, it's a little bit. This is definition. Which of the following is not required for PCM generation? the pulse code modulation requires sampler, quanticizer, and encoder. So it's these three things by the definition. Sampler, quanticizer, and encoder, you don't need a symphony.
So
Pulse code modulation.
what was the, how'd you get the answer for the 13?
Oh, we have our 8 kilohertz sampling rate,
Uh-huh.
and we have 6 bits of data, so 6 times 8 is 48.
Let's see. It's
Per second.
times,
Oh yeah, sampling 8.
times something. Yeah, that's not right.
Columns 15 through 18 are concerned with delta modulation.
Porque, o sea, it was just the. That's the definition.
The first correct 9 transmitted signals are.
If I did the gallery.
Sorry, Theo.
By the first
Well,
9 different signals.
What the hell?
You're starting at a reference point. The reference point is right here. And then the first trigger goes down, so it's -1. Next trigger goes up, +1. Next trigger goes down, next trigger goes up, next trigger goes down, next trigger goes up, down, up, up. That's why it's 8.
Awesome.
So these are triggers, not where you start here. But this is a reference point that could have started a long time ago.
Yeah.
So you start at the next trigger, which is 1. At least that's what I'm thinking. That's the only reason I think it's 1. It's 8. Is there something that's directly inverse of this?
Yeah, that's
second
one B.
Second is directly inverse.
Oh,
Oh, but the last thing.
Oh, yeah.
the last one, same, yeah.
The last one is
Negative
-1
one,
plus
yeah.
1. So
No.
this is just shifted to the right once.
All ones.
Yes, it's yeah.
Knowing me, I would
So-
probably choose that one.
If you choose A, that means that you're not counting where it started. If you choose B, that means you're counting where it started.
Yeah.
But the answer here is A. So, I guess you don't count where you started.
Don't count when you start. Basically go off the triggers.
Yes. After T equals 0. Yeah, I mean, if T equals 0, because nothing happened. Slope, overload, and delta modulation happen as shown above. You see that this is rising a lot faster than this can rise. So instead of showing a nice sharp up, it's showing a line. For a fixed sampling delta modulation, what is the general method to overcome the slope overload? So you cannot increase the number of samples per second. What can you increase or decrease? In this case, the answer is D, which means that you increase the weight of the change. But then in this case, if you were to do that over here, it would be like higher. So one of the ways to overcome it is to increase the weight of the slope. Limit MST, limit MT. You can't limit your message signal. That's what you're starting with. You can't change your message. Now I'm not sure what needs to be. But in order to overcome the slope overload, you could just change the amount of changes. It happens every time you change. As in, make this bigger. I guess this is MST, which is the
Make it wider.
Huh?
Makes it wider or what?
I don't know. MST. I'm guessing this is just. I'm guessing this is the signal. MST is the modulated signal label. So you can't change the modulated signal or the message. That's the trigger. So instead of taking 1, 2, 3, 4 to get to MT, it would only take like 2 if you were to double it. You know what I mean? slope overload and level modulation happen, choose the best possible case of MT. I guess,
Perfect.
Yeah,
I guess there's,
I don't know. The slip overload.
Well, isn't it because unit step function?
this would be a height of 10.
Yeah.
Oh, yes, MT, particular.
So this is just a message signal of 100.
But it doesn't show.
So T0. Yeah, what's it doing? And
T0 is just when this happened. So choose the best possible case of MT. So when the message signal is just
Is
one
that
line,
any step? Is that a step
Yeah.
function?
when the message signal is 10 hertz with an amplitude of 10. Again, 10 hertz with an amplitude of 10. A flat line with an amplitude of 10. Or and equals 100. Oh, okay. An amplitude of 100. The best case scenario would be this one because once it reaches here, it would just be a line. If it were this one, it would take such a long time to get to the 100 where it starts working. In this, it would be like really difficult to plug. So that's why the answer is MT equals 10 V2. Make sense? Sense? I can start over with this one. Look your shirt, by the way, where'd you get it? Walmart? Yeah. So, this possible case of MT is when it's just a flat line and it's not that big. It's also a flat line that's gonna take forever to reach the right tone. ¿Qué más? Generally, what is the advantage of adaptive delta modulation compared to delta modulation?
Yes, these questions.
I guess it's just a definition you have to memorize.
Yeah,
I mean,
overload, I guess.
I'll just remember that.
Like all the,
Just remember all the multiple choice.
yeah.
Yeah, I would write them all down in the cheat sheet.
I didn't, I even got
God,
it
why
wrong.
What is one disadvantage of carrier suppression in a single sideband phone transmission? Carrier suppression. Choose a true statement for single side bandwidth. I guess we just memorize that too.
Yeah.
Well, what if they gas like double sided or something?
So that's why you write down all the answers.
Disadvantage of carrier suppression.
And I don't think, he wouldn't ask me about those sided. He already says it on that shit.
Oh, maybe. Single sideband phone transmission.
Maybe I should start working on that.
More complex receiving input than must be this. I guess.
So it's,
You know what a single sideband and double sideband is? When you have two signals like that, the carrier function. You're using this and this as one sideband. This is the lower sideband. Lower sideband. This is the upper sideband. Upper sideband. So you could just use one single sideband, lower sideband, because the rest of the information is over here. But it would cost more complex receiving equipment just to pick up this side of the sideband instead of the whole thing. You know what I mean?
Oh, yeah.
So that's probably why. So the following has the highest bandwidth digital for digital telecommunication. I guess just the higher you go, the better. T4.
it was the
T4.
Telecom, T4.
Cycle.
Everyone knows that T1 is best worldwide, world champions.
My God.
I was hoping you'd catch it. I was like, you look like you play League or you know that.
I stopped playing.
But did you watch the finals?
Yeah.
Yeah, we watched it over here, bro.
Seriously?
Me and my brother and sister, we went into this room right here, the little auditorium.
You do that?
Nobody stopped us. Nobody showed us. We got popcorn, we got drinks,
Oh,
pizza, it was awesome. They're like 20 and 22,
Cuando
it's not cute, it's just.
it is cute, that's your sibling.
Yeah, you're spending time with them.
So it's, when was the world, 18? 15? When they search it? Yeah, I have a picture, I'll show you later. But yeah, T4, I guess, even though T1 number 1. Tan tan.
Yep.
Entiendo, güey. La curva de aprendizaje, güey, en este, pues sí, güey. Then you hit the multiple choices, pues sí. Abajo. Down.
Yeah, 25% to be
What about for the 4?
Yeah,
I like my chances.
I would have gone higher, but I'm just.
How many problems multiple choice?
Oh, it's a lot of them, actually.
Or what?
We were playing in full volume, it's awesome.
It's like one whole.
Turn off the lights. Oh,
Multiple choice was more, it was only 5 or 6.
On the last test.
Oh, no, but the last test.
So I bought them some markers like the ones I have, that's the thing you get. You think you like? it?
Yeah,
And you already used a lot of color in class.
yeah, I don't know who it was.
Oh, do something for you. Oh shit, there's chats.
Hey.
There's chats.
So people saying stuff in chat, I mean. Gotta go, thanks for reviewing, I'm gonna hop off. Alright, Hector, thanks for showing up, I don't know if you can hear me.